The Henderson-Hasselbalch equation is an equation that we often use to calculate the pH of a buffer solution. A buffer solution consists of a weak acid and its conjugate base, and in some cases it'll consist of a weak base and its conjugate acid. Buffer solutions are typically used to resist drastic changes to pH. The Henderson-Hasselbalch equation is as follows, where pH of the buffer solution is equal to the pKa of the acid in the solution plus the log of the concentration of the base over the concentration of the acid of the buffer solution. If we rearrange this equation, we can also get a ratio between the concentration of the base in the buffer solution over the concentration of the acid in that same buffer solution. Since the equation can be rearranged to be log of the concentration of the base over the concentration of the acid is equal to the pH minus the pK of the acid in the buffer solution. Note that the physiological pH is typically around 7.4. So it ranges between 7.35 to 7.45, which is the typical pH of human blood as well as other bodily fluids. At physiological pH, most amines will typically be protonated, and an amino acid will be found in the ammonium carboxylate form. As an example, alanine, which is shown here, the nitrogen or the amino group is protonated, and the carboxylate group is deprotonated. So we have a carboxylate and an ammonium form for the amino acid. Although organic chemists don't use the Henderson-Hasselbalch equation too often, I wanted to show you an example of how this equation can be applied to buffers. In general, we use the equation to solve for different terms within the equation. For example, the pH of the buffer, the pKa of the acid in the buffer, the concentration of the base, the concentration of the acid, or the ratio between the base and the acid. In this problem, we're going to calculate the percentages of the neutral and protonated forms of pyrimidine. In other words, the ratio between the base and the acid in this buffer. Pyrimidine is a molecule that we previously discussed, which has 2 nitrogens and 4 carbons. It is an aromatic compound. The conjugate acid of pyrimidine is pyrimidine with a proton on one of the nitrogens and a positive charge on that nitrogen. It actually doesn't matter what the structures of pyrimidine and the pyridinium ion are as far as solving this problem. In this question, we're going to be dealing with a solution of pyrimidine that is 0.001 molar at a pH of 7.3. As you'll see in a moment, the concentration of pyrimidine actually does not matter since we're going to be solving for a ratio. The pKa of the acid in this buffer, in other words, of the pyridinium ion, is 1.3. Here is one form of the Henderson-Hasselbalch equation. If we plug in the pH, which is given in the question, is 7.3, and we subtract the pK of the acid, which is 1.3, we'll solve for 6. Next, we're going to take the anti-log of both sides of the equation to get rid of the log on the left side. That means we're now going to have the anti-log, or take the anti-log of 6, which is 10 raised to the 6. What this is telling us is that the ratio between the base, in other words, pyrimidine, and the acid, in other words, the pyridinium ion, is 10 raised to the 6 over 1. In other words, there are 1 molecule of the pyridinium ion for every million pyrimidine molecules. So virtually at this pH, 7.3, all of the pyridine molecules will be in the neutral form rather than in the acidic form.